Today's lesson is called integration. You know that if you have a function like f of x equals x squared, then f prime of x, the derivative of that, would be 2x. Well, today we're going to learn how to take the antiderivative, which means we're going to go backwards. So if I give you a function f of x, then I want you to give me what the antiderivative of this is. So say f of x was equal to 2x. Well, we use capital F of x to represent the antiderivative, and we have to use the opposite process. Since when we took the derivative, we multiplied by the power of 2, here we're going to divide by 2, so it would be 1/2, multiplying by a half is the same thing, times our 2x, but then we're going to add 1 to the power, because here we subtracted 1, we're going to add 1, and that's going to give us f of x equals x squared. So the basic idea here is add 1 to the power and multiply by the reciprocal of the new power. The only thing is, what if my original function had been x squared plus 5, or x squared minus 8? All of those would have a derivative of 2x. So when I take my antiderivative of 2x to get x squared, how do I know it shouldn't be x squared plus 5 or x squared minus 8? Well, a better way to write the answer, is x squared plus capital C, where C could be any constant. It's called the constant of integration because the process of taking antiderivatives is called integration. So, we have a symbol that we use for the integral, which is one form of integration, and it looks kind of like an S, but a little stretched longer. So if I have this in front of something like 2x, you'll also have at the end of it a dx. These go together always kind of like a grouping symbol. This dx here is kind of like when you do a d dx. It tells you what your independent variable is that you're integrating with respect to, which we'll get into some more advanced things with that later on, but not to start out with. So this notation, and this would match the independent variable in the problem. So if you had like a 2t, this would be a dt. So this variable here will match whatever the independent variable in the problem is. So this just means we're going to add 1 to the power and then multiply this expression by the reciprocal of this new power. So that's going to just be 1, which you don't actually have to write. Then we need a plus c. Always remember to put a plus c on your answer. That's going to be critical. Now, you're going to get a big long list of all of your derivative rules that you've learned so far and what they look like going backwards for integration. It's not really a new list to learn. It's kind of like when you learn to multiply. 2 times 3 is 6, so 6 divided by 3 is 2. As long as you know the original rule well, you should be able to go backwards with it fairly easily. So let's look at some examples of this process. Let's find the integral of x to the 4th dx. Okay, so the idea here is that we're going to add 1 to the power, so that's going to be x to the 5th, and we're going to multiply by the reciprocal of the new power, so 1/5. Then I need a plus c. Now keep in mind, you can always check your answer by taking the derivative and making sure that it comes out equal to the integrand, which is the argument of the integral here between the integral symbol and the dx. So if I were to take the derivative of 1/5 x to the 5th, I would multiply 5 times 1/5, which would give me 1, which I don't need to write, x, and then subtract 1 from my power to the 4th, so that does come out. So these are fairly simple to check by using the derivative rules you're already very familiar with. Let's look at number 2. The integral of the square root of x times 1 minus x squared dx. Now, we're not going to be messing with any product rules or quotient rules or chain rules for integration. There are ways to handle situations like that, but it's a little bit more complicated than it was with derivatives, and we won't be messing with that for quite some time. So what I always recommend that you do is simplify your integrand as much as possible before you integrate. So let's first of all think of this as x to the 1/2 power instead of the square root of x, and now distribute that into the parentheses. So it would be x to the 1/2 minus x to the, add the powers, 1/2 plus 2 is 2.5, or as an improper fraction, 5/2 dx. Okay, now I'm going to do my power rule backwards. So I'm going to add 1 to my power, so this is going to be x to the 3/2 power, and multiply by the reciprocal of my new power, so 2/3. And again here, this minus will just stay here. Add 1 to my power, so 5/2 plus 1 is the same thing as 5/2 plus 2/2, which is 7/2. Multiply by the reciprocal of my new power, 2/7. And then I need a plus c. And again, you can check this by taking the derivative of this that we just wrote and making sure that it gives you what we had as our integrand. And if you want, as I'm going through these examples, normally in class I would give you a chance to work some on your own before showing you how I do it and allowing you time to check. So it might be a good idea to pause the video and give it a shot. Here's the integral of x to the 6th minus 3x cubed plus 1 all over x cubed dx. Now, like I told you, there's no quotient rule, so we need to simplify this integrand. So the first thing I'm going to do is take every one of my terms in my numerator and divide it by that denominator to simplify, oops, that's a plus, my integrand. Okay, so x to the 6th divided by x to the 3rd, that means we subtract the powers, that should be x to the 3rd. These divide out, so minus 3, and then 1 over x cubed is x to the negative 3rd power. Now I'm going to go power rule backwards, add 1 to my power, multiply by the reciprocal of that new power, add 1 to the power. On this 3, the power of x is 0, so now it's going to have x to the 1st. And then multiply by the reciprocal of 1. The reciprocal of 1 is just 1. And the minus just comes on down to separate the terms. Alright, x to the negative 3, add 1 to the power, that's going to be negative 2. Multiply by the reciprocal of that, negative 1/2. Then I need my plus c. Don't forget the plus c. You will lose points on quizzes and tests, in the AP exam for not including your plus C. And probably they would not leave a negative exponent in the answer. Probably be more like this, but either is really acceptable. They're algebraically equivalent. Okay. Next one, the integral of 5 over x minus 2e to the x dx. Now, let me show you something that you can do with integrals. This whole thing is the integrand, but whenever you have pluses or minuses, it is permissible anytime you want to split those up into separate integrals with the plus or minus between them. It's also acceptable to take a constant multiplier like the 5 here and the 2 here and pull those out and put them in front of the integral symbol. So this could be written as 5 times the integral of 1 over x dx minus 2 times the integral of e to the x dx. Okay, now here's your good pop quiz. The integral of 1 over x. If I rewrite that as a power, that's x to the negative 1. Add 1 to that, that's x to the 0. That's not right. If you'll remember, we had a special function that gave us a derivative of 1 over x. Do you remember what it is? Hopefully so. Hopefully you know your note cards. The natural log of x. So 5 times the natural log, and really we put it in absolute value bars, the natural log of the absolute value of x, because that shows everybody that we remember that the argument of the log must be positive, so it's not for any given x, minus, what is the integral of e to the x? Well, the derivative of e to the x is e to the x, so the integral of e to the x is e to the x. That's our easiest one. 2e to the x, and then I need a plus c. That's the answer. And again, you can check this by integrating, by taking your derivative. Okay, number 5. What is the integral of 1 over the cosine squared of x plus the cosine of x times the tangent of x dx? This is another situation where you're going to want to simplify your integrand as much as possible before taking the integral. Using some things from pre-cal, 1 over the cosine squared of x is the same thing as the secant squared of x. And then you'll remember that the tangent is the sine of x over the cosine of x. So these cosines can cross out. So this now becomes the integral of the secant squared of x plus sine of x dx. So, how do I integrate that? Well, what function, if I take its derivative, gives me an answer of secant squared of x? This is kind of like Jeopardy. Here's the answer. What was the question? Tangent of x. If I take the derivative of tangent, I get secant squared. Now, what do I take the derivative of to get an answer of sine of x? Negative cosine x plus c. So, this is really going to test to make sure that you know your derivative rules well, because now you've got to know them backwards too. You're going to want to study them both ways too. Even though you already have note cards of all of these with the derivatives, I really strongly suggest that you rewrite them on note cards as integrals. It will help you to be better prepared and study them both ways. Alright, number 6. the integral of 5 over x times the square root of x squared minus 1 dx. Wow, that looks complicated. Let's see here. The 5 can go in front. 5 times the integral of 1 over x square root of x squared minus 1 dx. And this is actually a really short, easy problem, because this is one of your note cards. What is that the answer to for a derivative rule? 5 times the inverse secant of the absolute value of x plus c. By the way, y'all, if you leave off the absolute value bars on a free response question on one of my tests, I'm not going to take off for that. I don't think that they do on the AP exam either on a free response. However, these types of problems would more typically be seen on the AP exam on a multiple choice question. And if it's a multiple choice question, they will have the absolute value bars in the answer. So I want you to be used to seeing them when you do your problems. Alright, number 7. Now, this one is a little different. This is going to be solving a differential equation. This is going to be basically like I give you the answer to the derivative, dy dx equals 1 over the quantity 2x in parentheses cubed. And I'm going to tell you that the original function, that's supposed to look like a semicolon, I'm sorry. The original function had y of 1 equaling 0. So this is basically like a point on the original graph. This would correspond to an x value of 1, y value of 0. Now, the object of this problem is to write the original equation, like y equals blah blah blah. So, how do I do that? Well, I'm going to have to take the integral of this. Okay? So, the first thing I want to do is simplify that, because it's not even simplified. 1 over 8x cubed is what that would really be. And when I'm going to integrate, it's going to be better to just have 1/8 times x to the negative 3 power, so I can use my power rule backwards. So, my y equals equation is going to be the integral of this 1/8 x to the negative 3 dx. So I can take the 1/8 out in front. And then I can add 1 to my power, which will give me a x to the, let me erase that, x to the negative 2, multiplied by the reciprocal of that new power, negative 1/2. Now my 1/8 is still here. Y equals 1/8 times negative 1/2 x to the negative 2 plus c. So this is y equals negative 1/16 x to the negative 2 plus c. And now I haven't used this point 1, 0 yet. This means when x is 1, y is 0. The reason they gave me that is it allows me to figure out what that c is. So if y is 0 and x is 1, I can find out what c is. Now what is 1 to the negative 2 power? Well, it's 1 over 1 squared, which is 1 over 1, which is just 1. Really, 1 to the anything power is 1. So this means 0 equals negative 1/16 plus c. If I add 1/16 to both sides, then 1/16 equals c. So the final answer to this problem would be y equals the answer that we got up here, negative 1/16 x to the negative 2 power plus, instead of c, the 1/16. So when they give you this point, you need to come up with the actual c value, because that's giving us a specific answer. Alright, number 8. Same kind, dy dx equals secant squared x minus sine x, and this time y of pi over 4 equals 1. So y will equal the integral of this function dx, which means y will equal the tangent of x plus the cosine of x plus c. Plug in this for x and this for y. So now I have 1 equals 1 plus the square root of 2 over 2 plus c. Subtract 1 from both sides, I have 0 equals the square root of 2 over 2 plus c. Get c by itself, subtract square root of 2 over 2 from both sides. Negative square root of 2 over 2 equals c. So the answer would be y equals, I'm going to take this and just plug in my c. Y equals tangent x plus cosine x minus square root of 2 over 2. Alright, number 9, dy dx equals 7e to the x, and y of 0 equals 2. We're going to say y equals the integral of 7e to the x dx. The 7 can go out in front. The integral of e to the x is just e to the x. Don't forget your plus c. Now I'm going to plug in 0 for x and 2 for y from this point. E to the 0 is 1. Oh, I've made a mistake. I hope you caught it. I forgot the 7. Okay, so 7 times 1 is 7. 2 equals 7 plus c. Subtract 7 from both sides. Negative 5 equals c. So y equals 7e to the x minus 5. Okay, here's our last example. It says, here is a differential equation, and it's hard to see. Why is it not writing? dy dx equals x squared minus x minus 1. Then it has a, b, c, d. A is to find the general solution to this differential equation. Well, the general solution is the y equals with the plus c on it. So y would equal x cubed times 1/3 minus x squared times 1/2 minus x plus c. There's your answer for A. The general solution has a plus c. But then B says, determine the particular solution to this differential equation if it contains the point 0, 0. So we're wanting our answer to travel through the origin. So I'm going to plug in 0 for x and 0 for y to figure out what c is. And if you look right here, 0 for x and y will result in a c value of 0. So it's just going to be 1/3 x cubed minus 1/2 x squared minus x. Now, that graph, that cubic graph, is shown right here. Sorry, I didn't do a good job of tracing that out. But for part C, it says determine the particular solution if it contains the point 0, 4. So if it contains the point 0, 4, that's 4 for y and 0 for x, which means C equals 4. Now 0, 4 is up here on the graph, so that's showing you this particular solution, which the equation would be y equals 1/3 x cubed minus 1/2 x squared minus x plus 4 for C. Now I've got to erase to make some more room. We'll leave my general solution so I can look at that. So for part D, it says given the point 0, -4. So if I put a -4 for y and 0 for x, that gives me a C value equal to -4. So the equation would be y equals 1/3 x cubed minus 1/2 x squared minus x minus 4. And that point is down here on the graph, so that gives this solution. Now, these particular solutions are drawn on a graph of what we call slope fields. Okay? This is a slope field. And a slope field is a graphical display of the solutions to a differential equation. So if you kind of trace through and follow, like if you drop a coin in a swift current, it's going to travel with the current for the most part. These slope fields kind of show you the path that different solutions would take depending on what point it's going through. So there's an infinite number of solutions to a differential equation because C could be really any number. So we see, I could have had a point going through 0, 8, and it would have been up here following more of a path like this. And we're going to work more with slope fields later on this year, but this is just kind of an introduction to kind of getting an idea of the way they look. In your homework, you're going to have some problems with slope fields. All I want you to do with them is match. Okay, they're going to give you they're going to give you a differential equation, a dy dx equation, and you're going to have to match it to the slope field that it could actually work for. So if you, some of you are more graphically oriented than others, but if you take the antiderivative or integrate this function to get the y equals equation, not that, this one with the plus c on it, you should see, like for example here, this is a cubic equation. Well, if you try to follow the paths of these slope fields, they're tracing out cubic equations. So a lot of times just by knowing your parent functions you can kind of figure out which one is which. So just matching, you don't have to do any graphing or anything else with those. So welcome to the world of integration, doing derivatives backwards. Study your note cards. You need to rewrite your note cards with all of the integration rules done, and study them that way in addition to continuing to study your derivative rules to be adequately prepared for upcoming tests and for the AP exam. Have fun!